Hello everyone, thank you for joining the presentation. My name is Aral Hekimoglu. Today I will talk about our paper titled Monocular 3D Object Detection with LiDAR Guided Semi-Supervised Active Learning that we wrote together with two of my supervisors, Schmidt and Alvaro Marcos-Ramiro. First, I would like to start by giving a bit of an overview about the problem and our motivation for the paper. For autonomous driving tasks, the tackling locations of nearby objects are quite important. Here there are multiple sensors that can be used, which could be LiDAR, stereo cameras, monocular camera, which offers a cheap alternative, but it lacks the depth information. So typically, the monocular camera is quite a common sensor deployed in autonomous driving. But LiDAR is also widely used during testing and for labeling purposes when you want to label the 3D boxes in the 3D space. So therefore, we assume that we have access to LiDAR during testing and the preparation period, but during deployment we only use the monocular camera. So the question arises of how to utilize the LiDAR data during both the data selection but also the training of the monocular camera. To utilize LiDAR during training of monocular 3D detector, some recent semi-supervised learning methods can be used. In these methods, predictions of the LiDAR on the unlabeled data are used as additional pseudolabels to train the monocular 3D detector. However, we observe that the predictions of the LiDAR can be erroneous, especially in areas with high LiDAR data uncertainty. For example, here at the back, the blue LiDAR prediction cannot predict the length of the green ground truth because it is in an area with low point cloud density. To reduce the effect of this error propagation from LiDAR to camera, we propose to scale the effect of training with pseudolabels by the aleatoric uncertainty of the LiDAR. So predictions with high LiDAR uncertainty will have a lower effect on training. Active learning methods are widely used as a strategy to select which of the unlabeled samples should be labeled. One of the most common ways is to use the uncertainty as an estimate to rank the samples for labeling and pick the samples with the highest score. However, with ground truth lacking, these methods typically cannot fully capture the error in the predictions. For examples here, samples with on the right for the bike rider have low uncertainty, but they still have high bias, and this cannot be captured by just using the active learning methods, traditional active learning methods with uncertainty. To additionally capture the bias, we propose to use the LiDAR predictions as pseudolabels and extend the traditional uncertainty-based active learning with this concept of bias. We combine our two proposals in a framework called Monocular, which consists of a training phase using our semi-supervised training that is scaled by the LiDAR's data uncertainty, and a selection phase using our proposed bias-based active learning strategy. Here we have the training dataset which goes through training, and with the dashed blue lines we have the semi-supervised training as well during the training phase. And then during the selection phase, we select samples from the unlabeled data pool. The selected samples are then ranked and sent to the annotator, which labels the unlabeled samples with additional labels and adds it to the training set. In the training phase, we have three main steps. First, we train the LiDAR teacher detector, where we adapt the training to incorporate the aleatoric uncertainty predictions. This is achieved by predicting not just the mean, but also the associated uncertainty for each of the regression parameter. And then we modify the loss function as shown here. Then we use the sum of these uncertainties in a single teacher aleatoric uncertainty score. This score is then used to define the confidence of each LiDAR prediction shown as Cx here. Finally, we train the student where we scale the loss by this confidence. In the selection phase of the monolith, we have three scores. First, we use the traditional uncertainty-based methods. We follow the deep ensembles approach and make 5 predictions per sample. The disagreement between these samples then define the epistemic uncertainty score. We then calculate what we call the teacher-student inconsistency, which essentially captures the bias in the student predictions. First, we take the average of the 5 deep ensemble member predictions to capture the average student, and we measure its disagreement with the teacher's predictions, which gives us the teacher-student inconsistency. To also have less samples with low LiDAR confidence, so that they can be used more efficiently during semi-supervised training, we also use the aleatoric uncertainty of the LiDAR as an additional score. We sum these up and multiply with the aleatoric uncertainty of the teacher model to obtain the combined selection score as shown on the left. Here we show the active learning curve for our experiments on both the Kitty and the Waymo dataset. In the Kitty dataset, we use the initial 30% randomly selected pool as our initial labeled pool, and at each cycle add 10% new data. So we observe that our model reaches 6.32% better final performance, and our model is able to attain the fully trained performance, 80% of the fully trained performance, with just using 48% of the data. In the Waymo, we observe similar gains, where we have 4.54% better final performance, and we reach the 70% of the fully trained performance with just using 25% of the data. So in the Kitty, this corresponds to a 12% increase than the state-of-the-art CDAL, and in the Waymo, it corresponds to a 7% increase. In order to isolate the effect of our semi-supervised training strategy, we compare it against several baselines on the Kitty dataset. So compared to LPCG, which is the state-of-the-art, we are able to increase the performance by 2.02 bird's eye view average precision. And we are also able to surpass the monodistal by a margin. We also compare against some other monocular 3D detection baselines that are traditionally trained without semi-supervised learning. And here we show that we are able to increase the performance of Monoflex by 7.08 bird's eye view AP. So, in conclusion, we proposed a novel framework which consists of a coherent selection and a training phase. In the training phase, we show that we can identify the potential error propagation from the LiDAR teacher to the monocular student and propose a way to scale the effect of these pseudolabels. In the selection phase, we extend the current active learning selection scores that are solely using uncertainty by adding the bias and using the teacher-student paradigm in the active learning by incorporating the inconsistency between the teacher and student. By these results, we end up both as state-of-the-art in active learning, where we increase the data saving rates by 17%, and also in the semi-supervised learning, where we increase the bird's eye view average precision of the state-of-the-art by 2.0. Thank you for listening to the presentation.